Bismillahirrahmanirrahim. Assalamu alaikum, dear students. Welcome back in direct design method. Students, this is lecture number 12, and basically I have uploaded 11 lectures total on direct design method. But in this lecture, that is lecture number 12, I am covering a different example, and this example is basically related with the beams. Okay, when you have beams on your periphery, or you can say you have edge beams and interior beams in slab system. So how we can use the DDM method? Although this method is basically skipped from the in our course, okay, which is taught in UT Peshawar, but because this is a little bit time-consuming method, a little bit greater amount of mathematical work involved in it, so we use basically the ACI movement coefficient method, which is more easy than this method. Okay. But although this is a demanding lecture, one of my friend basically request for this method to please sir post some lecture on DDM method, which basically involve beams. So let's see what we have in this in this example, that when we have a beam. Okay, so you see already I discussed this before I start this example. You must know I have uploaded a complete explanation of direct design method, 11 lecture this playlist includes. You must watch these 11 lectures to understand this method. Especially you have to understand lecture number 1 and 2. Okay, because in that lecture I basically explain so many things which is related to this example. Okay, so I have already explained these limitations. The only important thing that is this factor, okay, that is alpha 1, and you will see this is the relative stiffness, and I already explained this in my lecture number 1 and 2. Basically these are the conditions which is imposed when we have different panels, or we have edge beams and interior beams, how we calculate basically the thickness of the slab. So basically I explained all these terms in my lecture number 1. This is important. Remember, we have an edge beam which is known as perimeter beam, and we have a T-beam which are the interior beams. So for an edge beam we have to calculate moment of inertia, and for interior beam we have also need moment of inertia. It is denoted by IB interior, IB for edge beam. So this is, remember, this is very important point to be remembered, that in this case basically the moment of inertia of this section is basically BW HW cube, okay, divided by 12, and you see we have cantilever this portion and this portion, so we basically multiply two multiples, and similarly we have one portion, so for this purpose we multiply 1.5. This should be remembered. Similarly, section for IS and IS interior and IS edge, this is the slab, moment of inertia of the slab for edge slab, basically for edge slab, or you can say your ends panel, or you can say your exterior panel. In that case your moment of inertia will be denoted by IS, and it is calculated by you see the length and its thickness. Similarly here you see the width of the section is L2 by 2 and L2 by 2, remember, and this is very important to understand. Okay, and the other thing are the same column strip, middle strip. And one thing very important, L2 is that direction. Basically if we start the analysis in north-south direction, so L2 will be perpendicular to it. If we start the analysis in the north-south direction, then L2 will be perpendicular in this direction, and L1 will always be along the analysis direction basically. Okay, that is the span length, and the rest of the thing is same. Okay, that is the static moment. This is very important to understand. Okay, if you have circular column, let's say you have a circular column, you have to modify that circular column into a square column, and the side of that square will be equal to 0.89 times of h. And similarly, if you have a pentagon shaped column, you have to convert, you have to modify them into a square column, and its side will be, the square side will be 0.93 times of h, and you know h is the height of this pentagon. Similarly, if you have a square column but that is a rotated shape, you have to modify them in square, in a right square, okay, and h will be now this one. This is very important, okay. if you are facing such shapes of columns, so you must remember it. Okay, the next thing is this one. Okay, the only difference between a flat slabs and a beam supported slabs is this, the difference of coefficient. Okay, so in the DDM method, you see you have 1, 2, 3, 4, 5 cases, and we have different coefficients. We have to use this in we have to understand these coefficients like in this shape. Okay, remember, we have exterior support, we have interior support, interior support. Remember, the moment which is right here is called exterior negative moment. The moment which is right here is called interior positive moment. I think so. Interior positive moment. And here we have interior negative moment and interior negative moment. And here we have interior positive moment. I think so. This is called exterior negative moment. This is called exterior negative moment. So the first case is this, that you see when you have no restraint. Let me show you this in the Nelson book. These are the cases. If you have a Nelson book, you can search these coefficients and you can see these. Remember, when you have no restraint means when the slab is just over a masonry wall, or it is just only placed over a column, not jointed with it firmly. Okay, so in that case, you see what we have, the coefficients 0, 0.63, 0.75 and these. Okay, if you have a full restraint, mean that you see you have a full restraint, like a heavy beam here, a heavy column there. So in that case, you see the coefficients are 0.65, 0.35, only two coefficients, 0.65 for negative, 0.35 for positive. If a slab with beam between supports, this is important. This is the case on which we have to do example on it. Remember, when you have beams all over the slab system, okay, all over the panels which is covered by beams. Let's see, this is the example. We have perimeter beams, we have interior beams. So in that case, we will use these coefficients. And today's example is basically we will use these coefficients. Similarly, here you see that when you have no beams. So already we have covered example number 1 and example number 2, 3, basically lecture number 9. I have covered 2 examples on these coefficients. Already we use it, we are familiar with it. And edge beam only. This is the case, remember, this is the case when we have only edge beam. Remember, when you have only edge beam and no interior beams. Okay, no interior beams. So in that case, you will use these coefficients. Okay. So in transverse direction, this is the beta. This is also a torsional stiffness, and to calculate it, we will use this formula. Now, what is C? You see the C value is, understand this C value. Okay, we will use this in example. You see, this is edge beam. Okay, so in edge beam, x1 is the width, y1 is the height. Similarly, the slab portion is denoted by x2 and y2. And you see x1, y1, all these distances are used now in this formula. We will calculate C. This is important. One thing most important, you have to understand it. Okay. Remember, this cantilever portion from the center line should be equal to this much distance, okay, or it should be up to this, okay, you have to minimum value. And similarly, this cantilever will be, it should be HWR less than 4HF, okay, so we will use this, okay. Now, the other things are these coefficients, and you will see how we use these coefficients, okay. And the most tricky part, I think so, is that because here we have to make so many interpolations to got the values. Although we can use these tables as well. Okay, so these are the same coefficient which we will use in example number 1, 2, 3. Okay, and the thickness basically our slab system is basically supported by the beams. So the thickness is a matter, and already I have uploaded 2 lectures on it. Lecture number 1 and 2. Basically, I explain these coefficients. Okay. Similarly, these coefficients can also be used, and these are the limitations of steel. Okay. And remember, there are some points which is regarding to the detailing. Okay, I have recorded lecture number 7 and 8, I think so. A full explanation, more on you can say almost 1 hour lecture. Okay, so I explained the full detailing of a DDM flat slab system. But here, remember, here we have beams. Okay, reinforcement, the torsional reinforcement, I also explained this in my those lectures, and these are the cut-up bars points. Okay, although you know this L by 3, L by 4, but in the case of flat slab system, you have to use these coefficients. Okay, these are for top, okay, and these are for bottom. But in column strip, in middle strip, top bars will be this one and bottom bars will be this one. Okay, so this is important. Where you have to provide lab, you see the lab. Okay, and next, this is the example. Okay, so let's start the example. See, we have the same example. We have the same 20 feet span. We have same half column strip, half middle strip. Okay, you already know this. Okay, you already know this. And we have to choose this interior frame and similar exterior frame, similar in this direction interior frame and exterior frame in north south direction. We have same 14 by 14 inch column, same panels, and height of the building 144 is the PSF loading. You have to check your limitations, and now we start our design. Okay, let's assume our beam size will be this much. We will assume, okay, this is not fixed. You can use, although we have to use 14 inch, but you can change this 20 inch to 24 inches, 18 inches as you wish. Let the column dimensions already decided. Slab thickness. To find the minimum slab thickness ACI equations, basically in this case I already uploaded 2 lectures. Lecture number 1 and lecture 2 is regarding to slab thickness. So you please watch those lectures. Okay, you will know, because in this case the calculation is a little bit different. Okay, and the thickness which I use here is 7 inches. Clear? The effective width for beam. Now this is important. Already I show you that we have a T beam. Okay, we have a T beam and we have an L beam. So what will be the effective width from the center line? This one and this one. Okay, I already explained this. So effective flange projection, minimum of 4 chip or HW. 4 chip is equals to 28 inch and HW is basically 13 inches. Okay, you already know HW. HW is basically the rep depth. This rep depth. Okay, this is 13 inches. So the minimum value is 13 inches. So this projection is basically 13 inches. Okay. Now therefore the effective flange projection is 13 inch. Now we are checking B effective BW plus 2 times the effective flange projections. Now 14 plus 13, 40 inches, and for H beams this is 27 inches. So this is 27 inches. Sorry, this is 27, and in this case it is the total. This, okay, the total one will be 40 inches. Okay, B effective. You already did the analysis of T beam and the L beam. Okay, so the same principle you see here. The total width of the T beam will be 14 inches. Okay, and here you see this is 13 inches. The thickness of the slab 7 inches. The rep depth is 13 inches and BW. So this is, I think, so easy. Now here we have this table, and this table is very important to understand. Okay, what we have this in this table, you see panel lengths 25 feet, 20 feet, 25 feet, 20 feet. Okay, 25 is basically in longitudinal direction, 20 in transverse direction. Similar, 25 in longitudinal and 20 in. One is basically for interior, while interior slab, okay, and one is for exterior slab and exterior, okay, north-south direction and east-west direction. Panel widths, if you are taking 25 feet your length, then your width will be 20. If you are taking 20 feet your length in north-south direction, this 25 will be now your width. Okay, so that is the principle. Now, if you are taking 25 feet in for exterior column, okay, for exterior frame, let's say, for exterior frame, here we have columns. So if you are taking 25 feet, okay, your span length, then remember this half will be now your width. This half will be now your width, and that is 20 divided by 2, so 10, and up to center you have to count it from that edge basically. Okay, so that is 10.6 inches. Similarly, if you are taking 20 inches for exterior frame, then 13 point, that is 25 divided by 12 divided by 2 and plus that h by 2, I think so. So this table is basically 20 feet, I think so. These are clear. Okay, slab height, already this is fixed. Now this point is important, moment of inertia for slab. Okay, for slabs. So you see, all designations is right down here. Okay, so you don't need to be confused. Moment of inertia for interior slab, moment of inertia for interior slab, moment of inertia for exterior slab, and moment of inertia for exterior slab. Okay, so BHFQ divided by 12. Now B is basically, I already explained this in my initial, when I was started this lecture, and I already explained this here. You see this one, this is basically my B. Here for edge, or you can say for exterior, this is L2 divided by 2. So then I will use 10.6 something. Okay, so you don't need to be confused. Okay, here we have BH cube. So your B is basically 20 for interior. For interior your B is 20, H is 7 and 12. So you do the calculation, you got this one. Okay, B is these two values. Similarly for this 25 will be your B, HF, and similarly for this 10.6 is your B and HF. That is all about for exterior frame. These two are for exterior frame. So in that case basically L2 divided by 2 is becoming your vector. Now for moment of inertia beams, so I beam for interior frame and I beam, moment of inertia for beam for exterior frame. So already I explained this 2 and 1.5. If you have two side cantilever, in this case you have to multiply 2, and if you have one side cantilever you have to multiply 1.5. BW is the width, that is 14, and HQ basically the depth of your beam. So you just plug the values, you got these two answers. Okay. Now these are your moment of inertia. The notation is now alpha interior 25 means the alpha value in the direction of 25. Similarly, the alpha, this is the relative stiffness in the 20 feet. Okay, and this is 25. So these are the relative stiffness. Okay, for exterior and for interior frame. Now how they got these values, you see column number 7, basically this value divided by column number 5, this value. Okay, and I already explained in lecture number 1 and 2, you can see how I define these things. And you see here what are ratio of moment of inertia of exterior beam to moment of inertia of 25 feet long exterior slab. So I think so there will be no any kind of complexity and difficulty basically you have to face. This is easy. Okay, now alpha m, okay, this is important. You have to average these values 1 2 3 4. So average them, you got your alpha m, that is 2.75. okay. Now beta is what? Beta is larger clear span to the smaller clear span, and I already explained this in lecture number 3-4, I think so. Okay, when I discussing example number 1. So you don't need to be confused in these values. Dividing by the smaller one, clear spans. Remember, clear spans. This is important. Clear spans. Okay, you got 1.27. This is beta value, and we need. Why we calculating? We need these values. Okay. In later stage you will see, according to given conditions, since alpha m is greater than 2, following equations apply. Now these are checks for H. Okay. When we have parameter beams, or you can say H beams and interior beams, so alpha m limitation is that your alpha m should be greater than 2, but it should be less than 5. Remember, its range is basically greater than 2, but should be less than 5. Okay, this is the limitation. So as you see, our alpha in value is greater than 2, so that's why we are using now this equation. ACI 9.5.3, you can see this, okay, and in Nielsen book this is also explained these conditions. There are different conditions, remember, and I thoroughly explained these points in my lecture number 1 and 2. So please watch those lectures, I already mentioned you, okay. So alpha f and alpha beta value, we already calculated it, okay. So because when the slab supported by beams, the thickness of the slab is basically a matter, okay. You see here we got 6.67 and 7 inch. Now we got it already in the first stage of calculation. We assume h, that is 7 inches, but here you see that they will confirm, this equation basically confirm that our assumed thickness of the slab is okay. Okay, we can go forward. If it is greater than, then we have to revise the calculation. This is important, okay. You have to check your calculation. If you are assuming something, then you have to check it, okay. This is important. Now the next thing is that already in example number 1, if you see in those lectures, we are using h if is 10 inches. Now this is the importance and this is the benefit of providing your beams, that it will decrease your slab thickness, okay. This is the advantage. You have to calculate your service load, dead load and factor load. Remember, this is your factor load, okay. The 4 frames are required to be analyzed for this specific slab system. Only two of the frames will be analyzed and designed for demonstration purpose, that is, okay. 2 frames, one is exterior and one is interior, in east-west direction. Remember, 2 frames is basically here we are designing. So analysis for EW interior frame, you already know what is L1, what is Ln, what is L2, okay, what is your stress fit, you already know. What is M0, you already know this. Now this is the part which I have to explain, okay, because due to beams you have to change your coefficients, okay. Already the other calculations are same, you have to just change these coefficients. Now exterior span, you see, okay, we have 2 spans already. Let me show you where I have my example. This is okay, I think so, not this one, this is not one, I don't have that example, but I think so in Nielsen book I have. Here you see in this example, okay. So basically what I have 25 feet and 25 feet. Now let me show you. Remember, this is my exterior panel, you can say, and this is my interior, okay. This is important. Now remember, what will be the coefficient, longitudinal coefficient will be here. What will be the longitudinal coefficient for this exterior negative moment, for this exterior this is exterior positive moment, and this exterior negative moment? What will be the coefficient for, in this case, that is the interior negative moment, and similarly this interior moment, and similarly here, okay. So in case of flat slab system, you already know this is 0.26, this is 0.52, and this is 0.75, but here as we have beams, so these coefficients will be changed. And I already explained these coefficients, that when you have a beam slab system, okay, beam slab system, so your coefficients will be, in that case, I explained these coefficients here, okay. Look, slab with beam between supports, when you have beams, so you have to use 0.16 for exterior, 0.57 for exterior positive, here you have to use 0.7, here you have to use 0.65. So these are the coefficients, okay. Although in case of flat slab system these are different. This is the only difference between that example number 1 and example number in this example, okay. So you see the coefficient, these are the longitudinal coefficients. I just pick those coefficients, and this is my end panel, and this is my interior span. Remember, you see exterior span and interior span. The M0 moment you see here, similarly M0 moment you see here, Now you have to multiply 476 with this one, you got this one. Similarly 0.57 with this one, you got this one. Similarly multiply these coefficients. Now this coefficient will be with this one, with this one, with this one. You got these values. Okay. Now remember, this is LM, longitudinal moments. Remember, m naught times distribution factor. This is your distribution factor. Okay. And this is the longitudinal distribution moment representations. You see all the moments. Now the next thing is that you have to transversely distribute these moments. Okay. To transversely distribute these moments, you need torsional stiffness, beta. So to calculate beta, you need C. And you already I explained this formula. C is what? That is basically I explained here. Okay, x1, x2, I think so. Let me show you. Where is that formula? Okay. And there are some other these factors which basically here, I think so. I explain it here. No, not here. Let me show you. This one. Okay, this formula. Now what is 1 minus 0.63 x1? This one, that is 14. y1, that is I think so in our case basically it is 20 inches roundabout. x1, that is x1 cube, again these values, and you cube it and you have to multiply it, divide it. Okay, 1 minus x2, this is 7, y2, this is I think so 13 inches roundabout. Okay, so we have to use these. Now let me show you where we were. So here, now you see 14, 20 is my total depth, y, that is 14, my x 20. Okay, again 7 is my that h divided by 13. So already I explained that is my 13, and you did the calculation, you got your this C value, that is the torsional stiffness coefficient, and you see now beta T is what is C divided by 2 times of moment of inertia x interior slab. Moment of inertia, remember slab. Remember moment of inertia, your slab in 25 feet direction. Remember in longitudinal direction basically. So you have to divide things. You got 0.81, and remember this coefficient. This is very important. Next we have to already we calculate this alpha for interior in 25. This is in table here. You see this is L interior 22.7. Okay. So next we have to divide L2 by L1. L2 by L1 ratio we needed. I will show you 0.8, and you have to multiply this 2.7 with that ratio. You got 2.2. Now why we need these beta T value? Why we need this? These are needed to determine the lateral distribution coefficients. And here you see these coefficients. Now I will show you the most tricky part, you can say, of this example is this part. Okay, how you can got these values right now. Okay, this is important. Let me show you. For this purpose, you have two approaches. Either you can use the graphs, or you can use the appendix A4, which is in Nielsen book, or either you can use this table. Now let me show you this table, how we got the values, because by using this graph, I think so this is easy. You have to interpolate things while using those graphs. Although those graphs are easy, let me show you first those graphs. These are design aids, and here I have those graphs. This one. This one. Okay. This graph A4 will be used for this. Okay. So the first interior negative moment. Okay. The value which you have seen here 0.81 for interior negative moment. How they got this value? Basically, you see, this is my beta value, beta T value, and this is the values which are right down here. You see here, this is L2 by L1. So L2 by L1 is my 0.8. You have to go up and stay here. and my beta t value is 0.81. This is a little bit larger, higher value. Okay, so from here you can see the my value will be what, 0.81 something. Okay, this is my coefficient, you can say. Similarly, for exterior negative movement is a little bit tricky. It is not simple to got the value. I will show you by interpolation, but here this is simple. Okay, because in positive movement, for exterior negative movement, we have to use torsional coefficient, that is beta t. But in this case, while in this case we don't have to use that torsional factor beta. So let me show you the positive coefficient. So again we have to use again same value, and that is 0.81. If you are using the interpolation technique, okay, if you are using the interpolation technique, so let me show you that interpolation technique, how you can do the calculation from that table. Okay, so because to understand interpolation, it is, I think so, that is better for you. Okay, because okay, this one. Now see, for interior negative movement we got 0.81 coefficient. Now how we can use this, although we got that value from table, but from graphs. Now from this table, how we got that value? Okay, so the ratio in our case is basically you have to write down 0.5 here and 1 here, and the 0.8 value will be in between these two values. Okay, because the L2 by L1 ratio is 0.8, which is in our case. Now we have this case now. Okay, because our alpha f1 L2 by L1 ratio is more than 1, because we have 2.2 already. So now we have to use these coefficients. Now you see 0.6 versus 0.9, while 1 versus 0.7. Okay, this is clear. Now we have to interpolate this value. We have to interpolate this value. Okay, this is simple to interpolate. Okay, the interpolation is simple. X value will be what? How we can now got this value? So this interpolation is simple. I already did this calculation, and from 0.9 minus 0.75, okay, divide by this one, 1 minus this one, 0.5. okay, you have to multiply it with what value? With the difference of these two values. The difference of these two values, 1 minus 0.8. Okay. You have to multiply this. You got the value. Then you have to add up this value. Add up this value with this one, 0.75. This is the interpolation formula. If you understand this conceptually, so let me show you the concept behind this formula. Okay, let's say this is the line. I have 0.5. The value is 0.9. Okay, 0.9. And I have 0.1. I have a value 0.75. Okay, 0.75. Now we need to join these 2 points, and now we have to join these line in horizontal. Now here we have our required point, that is 0.8, and here we have to need to calculate this value. First of all, we calculate this x value, this x. That will be comes out from this formula. How we got it? Okay, we use similar triangular rule. You already know 0.9. We have to obtain this side. 0.9 divided by the distance. 0.9 minus 0.75 will give me that height. Divide by this whole distance, that is 1 minus 0.5. Then similar triangular rule are equals to this x divided by this distance, that is 1 minus 0.8. Okay, so you got easily x is equal to what? You just need to multiply this with this term. You got x, and then you have to add that x to reach this point, and this is the simple principle. And you remember, your this height will be now 0.8. 0.81. Exactly, you got 0.81. So if you are unable to read that graph, you can use this simple interpolation formula, and you will got your required value directly. Similarly for this case as well. But the most tricky part is now this, okay, because here we have to interpolate 2 to 3 times. Okay, now what basically I have did here, for this case, let me show you the calculation. Okay, 0.81, okay, for interior span. Positive and negative both have 0.81, and already from graph as well as from the calculation I show you. Okay, this 0.81 will be applicable for your interior negative movement as well as for your interior positive movement. If you are interested, because you see 0.90 here and 0.75 is here, so that's why you got the same value for positive and negative. But for exterior, we have to use now torsional factor, that is beta t, okay, for exterior. This torsional factor, why we are using, this is also a very important question, and I like to give you the answer. Remember, as we have an H column, remember, and we have H beam. Okay, so on H beam basically, and here we have a slab system. Okay, so this slab system is basically exerting torsional stresses. Okay, so due to that, basically we have to count for this beta. This beta is basically counting for that torsional stresses. Okay, and how we calculate it now, let me show you those calculations. This is a little bit tricky calculation. Okay, you see, we have two cases here. One, when this value is equals to 0, then you have to use this table. But as we are in this case, because our this value is 2.2, okay, so which is greater than 1.0, so that's why we have to use now this table. Now here you see you have beta t and beta t greater than 2.5, mean that our value, our required value beta t is 0.81. Remember, if you understand this step, remember the rest of the calculation is simple. Only this part is a little bit tricky. 0.81. Okay, 0.81. So beta t is our required value is 0.81. Let me show you. Remember 0.5. Okay, and then the next value is 1.0. Okay, now the required value of 0.8. This is our ratio. Now you see here 0.1. Here my beta value, that is 0, and here my beta value, that is 2.5, and my beta t value is 0.81, which is in between these two values. Okay, now the value of the coefficient basically for lateral distribution, again 0 is 1. Okay, and similarly for 1, again this is 1. Clear? Similarly for 2.5, you see 2.5 is 0.9. Okay, and 2.5 against 1 we have 0.775. Clear? This is important. This is important. Okay, this is very important. And okay, now what we have to do, remember 1 is same. This means the value which will be 0.8, you can say, sorry, this is not here. Already there is no slope. All this is a linear line, so that's why we will write down here 1. Mean that 0.8, 0 value will also be 1. Okay, because this is a linear line. But here is the problem. You see, this is 0.9 and this is 0.7. There is a slope line. Now we have to guard the value here, which is against 0.8. So if you interpolate the value against 0.8, you got the value here, that is 0.81 will be here. How we can do it? Basically, you have to use a same interpolation formula, okay, for this purpose as well. And I think so the calculation is simple. It is not tricky. You can use, let me show you, for example, this shape